screen. And so we have here in this talk, we have heard lots about autonomous systems and how to make them reliable, how to make them certified. But one thing that we didn't talk about was how to make them accountable. And from the people who are in the States, probably are not surprised about that because there is this big dark NSF call for designing accountable autonomous system. And I'm also very happy to report that on this call is one of my co-authors, Scott Shapiro, who is a professor at Yale Law School. So Scott, can you wave? And just that you don't take against him, why is he in the law school? He's also a professor of the law school who knows what is predicate abstraction, who knows what is Herbert model, but he also knows how to construct Danziger-Bachmeier models. So bravo for Scott. Now, jokes aside, so let me actually tell you a little bit more about how this project started, and I will tell you more, and then you will see how this project arose with all these amazing people on. Let me start with a simple example. So here, in all the examples that we have seen so far, what would happen was that, you would have a cars and they would actually stop where there was an obstacle. But what has happened now, we see the blue ego car is coming and it's coming to the intersection, and we see the yellow car coming as well. And what is happening, yellow car is giving the signal, and instead of turning, it enters the intersection, so the blue car crashes into it. So when we think about what has happened, we can explain, like the sensors of the ego car registered that there was this yellow car signaling that it will turn, and it's the logic decided to proceed forward. But then when yellow car did not in fact turn, the crash has happened. So you can say, okay, that's a reasonable story. It is consistent with observations that we have seen. But of course, question is like, is this story right? Is this exactly what has happened? Because now let me actually tell you two other stories, both of them completely consistent with data what has happened, but at the same time, it will totally change perspective on you and the car that is from you on the car and what has happened. The first one story is about reckless driving, which is like the ego car just comes to intersection and it doesn't care, ignores the turning left and right, drives to the intersection. So if that would be some human, you would say like, oh, it's some teenager trying to impress others. But the third one, the one in red, is actually saying something even very somehow disturbing. It says like, well, there is the car that comes to intersection, and then it actually is waiting for some other car to crash. Its only purpose is to crash the other car. Now, if you're in this car that is entering intersection in the green car, for you, it really somehow doesn't matter, right? You were crashed. The output is the same. But it does matter whether you were crashed by pure accident, whether you were crashed by reckless young driver, or whether you were crashed by pathological car. And what we are working when we want to somehow talk about this accountable software, we are working on distinguishing this scenario, because if you think about it, all these cars, they're autonomous vehicles, they are relying on the decision logic that is underneath. And we know that we cannot understand this logic. So what we try to understand is like, how can we understand better this decision logic, how it works? And actually, this is important because both from from legal or criminal activities, because if you assume for a second that was human, whether it was reckless, whether it was pathological, it was accident, you can immediately see the consequences will be different. But also we can watch from the engineering intervention. I mean, we all know that the decisions actually, it's hard to understand. I mean, there is a big push for explainable AI, but we are still not there. So if it turns out that your AI is maybe pathological, of course, from engineering perspective, you want to understand how to address this problem. So now let's actually think what would happen.
Question?
Yes.
Are you going to go into maybe the legal definitions of what reasonable, reckless?
I am coming to this. Right. Don't worry. And in addition, we have a lawyer on the call. Okay. If I don't say it right, he will help. Okay, but let's go what would be in the ideal world, in the world of, like butterflies and ponies, in this case, we would actually prove that code is correct. We would use our formal methods. We would actually prove that code is correct before deploying it on the car. And of course, we would verify that we have right decision-making process. But we not know, that's why we are here, right? We have shown that this is not possible computationally. So what we try to actually do is in our work is to explain what is after the event has happened. We want to actually identify responsible agent and its intentions. What's our intentions? And funny enough, it's like if that would be a human, we would kind of try to work backwards to say like, okay, why did actually, what it led to that event even to appear? And we will try to do exactly here in autonomous vehicle setting. So the proper formalization of what we are trying to do in this project is it says like we want to enable rigorous investigations of this computational decision that have happened using formal methods. And we actually want to, while we are doing this, we also want to meet the standards both of legal and philosophical notation of culpability, responsibility, and accountability. Now, I said that I will try to explain them more through examples of that the informal methods understand, but it kind of, if you're a non-native speaker, as I am, all these words maybe sound the same to you, but maybe to explain them. Culpability, and Scott, please correct me if I'm wrong, culpability actually means, mea culpa, right? There was some wrongdoing involved. So the person who actually is already involved in the process that is responsible for it. Like responsibilities means, of course, who is responsible, and accountability is like who can be held accountable in that place. So now let's actually again look at the situation that has happened. Right, we have our two cars crashed, and for a second, ignore that this was autonomous vehicle. Assume that this was just a human driver. You see a human driver in front of you in the car, and we actually try to understand, and let's assume we are in the court of the law. We try to understand whether it was, like reasonable car, so it was just pure accident, whether it was reckless car, which was just driving and being, like young and full of energy, or it was pathological car. So what we would do, here is the big picture at what I have learned from watching the series about laws or about lawyer series. It works as follows. So we have investigator and we have a subject. There is already established behavior about the subject. So for example, there is the history of that person that we are investigating. So we already know that the person repeated the same things before, or is doing it the first time. Then we would ask, a lawyer would ask various questions saying like, but what if you have done this, but what would be then the outcome? Did you know the following? Could you have done the following? So there would be the whole sequence of the questions where we would provide the subject with the, like what would you have done in this case? I mean, you turn, but have you seen that the car signal that it would turn? And then, like maybe we, as a human will say, no, I haven't seen, but can actually, then it's especially, can autonomous vehicle lie, right? So all this will be this loop, and after enough of questions, we would actually, the investigator will build interpretation and says like, okay, based on all these questions and the answers that I have received, I believe this is explanation of what is indeed has happened. And of course, now there is this question that's like isn't law, certain law should be, like very strict and, like clear, this and this and this should be happen. And we actually discussed this already in the coffee breaks many times during this week, that we actually saw that law is vague. It's on purpose vague, right? Because like, as Shankar pointed out nicely, there was a comment like, all you want to say, do not pollute, right? Like there is one big decision, but nevertheless, you won't have the things you should say, do not pollute. You will have like, do not do this, do not do that, and so on. So, like that is the same here. If you can see, we have like, law would be like, do not crash the other car. But why did you crash the other car? That is an important question. So now let's assume.
So there's a kind of further complication with an autonomous car, that it's made up of multiple components interacting. Some behavior that you see may be emergent, and they may not be a kind of locus of blame in such a system.
That's true. I mean, then you will see what we are doing is we kind of take currently the autonomous agent as in its code as a one component, and then like we just kind of use it to derive verification conditions. But then like when we will do more detailed analysis, then we could actually try to go to look more thoroughly and try to identify using our standard techniques where the blame is lying in which of the components. Okay, so that would be with the human, right? If we are putting the human on the court and try to understand what has happened. If we would have, on the other hand, autonomous vehicles, I will come into this, but like since we have a code, we actually want to work with something that we understand I will explain this into more details. Enough for now is that you see there is SMT, so clearly you can already know like, oh, you're encoding everything as a formula and you're asking queries. Yes, you're right. And I will head you towards that to understand how we are actually modeling this and how we are asking queries. So I just see there is something chat. Is this a question? No, that's
I'll let you know if
that's people saying bye. Okay, so now let's actually see first how we would model this. So first assumption that we are taking is like that we have access to agent's decision code, right? So the code is not a black box, its code is there, and that will assume program P is available. And also, that all these agents are actually logging everything that is happening, right? So they will log, what they have seen from the sensors and everything. This is logged. So we will actually, and this we will consider that this factual traces of what the agent log is actually available. And then you will see this will actually also influence how we are modeling the problem, because we are modeling is not from our perspective as someone who is standing from outside, but we are modeling from the perspective of an agent based on this factual trace. So now let's look into this factual trace and think what we can see. Like first thing, what agent sees, and by agent I mean this our ego car that was actually driving. Agent perceives environment, right? So we can actually model environment, but also agent sees its own state, saying like, okay, like we can encode this simply as formulas, right? I'm saying like, okay, I see the other car, its position, X position is 1.6, its Y position is 1.46, its signal is right, pointing to the right. I can see my own position. You see another formula describing where I am. So, like both states, like where I am and how the I see environment, that I can actually look in this logging trace. And from this, I can construct first order logic formula just as a statement of X explaining where I'm right now.
How do you model the temporal aspect of this?
We are not going yet towards temporal, right? We have a time.
So just the final state.
We have a time. It is just kind of modeling as like at the time position is this, at the next time position. So which means if we will want to use afterwards it's happened, we can actually just put this T1 is smaller than T2.
So it's like a log, you have the
Exactly. So all this modeling of the state is actually from taking this log and the trace and pulling down. So there was this postdoc in Jean Charles' group, who is actually, maybe you know him, Monkey, who actually had his also a small 1/10 of the formula, and then he explained us. So we really kind of played with his tool. We didn't play, he gave us access to the code, but not to the card. But now, so there we are. So we can model, right? I can model my world with the simple first order logic formula, and then you can suddenly see what I told you. And when I would ask you as a human, have you seen the signal? No, Your Honor, I didn't see the signal. But if you see that when you model the log, you will see that when you ask, have you seen the signal? You can say, yes, the ego card has seen the signal. It's not, like it cannot lie. And then actually you can reason about that. So now, I said, you asked whether we will talk about law and philosophy. Yes, we will talk a little bit. So let's actually see. But one thing that I also want to point out, when I was modeling, you remember we had investigator and we had car that is investigating. This definitely works with the human in the loop, right? So our current approach is like that we try to get all these things like what is intention simply by human, like having human. Human is there to ask questions that will help human to better understand what is intention of the car or what is intention of the agent that it's investigating. And one of the topics that we have definitely tried to understand better, and that I know that Scott is actually very passionate about, is that we are currently deriving intention simply based on our experience and knowledge. But one topic that we definitely want to address is that if we could kind of derive formalization of intention so that, okay, human still has to be in the loop, but maybe that we kind of try to reduce the burden. So let's actually see. One thing that I want to talk about also are counterfactuals, right? We have causality, intention, and responsibility. And we work or analyze them all through the concept of counterfactuals. So counterfactuals are, you probably all have someone who is constantly asking, but what if? What if? So this is actually what is counterfactuals, like in a very simplified way. Like practically, we know what has happened, but we want to check another. And what would happen if something has changed? Like, what would the car do if, like the other car didn't give a signal? So then we actually want to see the output of that. So causality is a very deeply studied in formal methods. We all know the work of Halpern and Judea Pearl. Judea Pearl even got a Turing Award for this. I think it is causality and probabilistic modeling of it. And if we try to just somehow briefly explain what this says, like there was the right signal that caused the ego car to move because like right signal kind of, if you looked at the sequence of what caused the things, like a car gave a right signal. Right, ego car thought like car is turning, so we do not care, decided to move, and because the ego car decided to move, that actually caused the crash. And how we model, you will see that very often this. If signal is none, assuming that our car is reasonable, if there wouldn't be any signal, the ego car would have paid. You can think about it just as a standard implication, although from what I understood, it's not just like A implies B, it is like you take A implies B in some sorts of environment, and if you kind of whatever is in addition, like when you have the event A happens, that this will lead to event B. So because there was a signal that there was no signal of intent of a turning, then the ego car would have waited. And another thing that I actually want to describe is responsibility, right? Because we now say causality, but then responsibility is like, we want to say not only which data led to this decision or this decision led to this outcome, but also was this decision, like in the purpose of doing this, like was it intentional? So you see, like it's not only why we did it, like because sometimes you will do things like by accident. Like maybe I have here a coffee and I will maybe push it and I'll accidentally spill it on the laptop, and this will be accident, but it will be, but if I do this on purpose, then actually it's a different way of responsibility, right? Here is, I'm really sorry, but here is like, okay, we have to settle this.
So from a legal definition perspective, responsibility must have intent.
Yes.
To assign responsibility, you have to establish intent.
I say yes, but Scott, can you confirm, did you hear the question? From legal perspective.
Yeah, no, can people hear me?
Yes.
Yeah, no, it's a sufficient. So what Ruzica is describing is like a kind of a hierarchy of responsibility. And so it's generally thought that if you intended the wrongful action, then you have the highest degree of responsibility, but you can still be responsible even if you did not intend. So part of the focus here is to at least understand like the clearest, highest expression of responsibility. And then the idea would be to then weaken things to, or in the case, add things to be able to understand other levels of responsibility.
Thank you.
So thank you. So now actually this is really great because you can see now why we do need an expert in the loop, right? For me, like formal methods can, right? For us, like, like our reasoning, like there is a program called derived formula called SMT solver, but it's actually from a legal perspective, it's not that simple, right? So that's why the responsibilities have a higher high levels of responsibility. Yes, there is another question.
So moving from what law says about that to like to the perspective of how you model that. I mean, I'm assuming just the distinction between something that is non-deterministic or deterministic will not suffice for defining responsibility, right?
So how we are modeling it is actually really left to human who is asking questions. What are we doing from a formal methods gang is doing? We are actually providing machinery that helps you to ask these questions. We will come to the loop. You will see then once we will better understand modeling, because I want to actually now also describe how do we model counterfactuals and the questions, and then how we actually then give these two queries. And that's why, again, as I said, like there will all the time to the talk will be caveat, there is a human in the loop, because simply us as a formal methods community, we do not have enough of expertise to ask the right questions. I mean, that's why we working together with the experts in the law, because we want to understand better, as I said, like our next goal is like that we try to see if we could even axiomatize intention, responsibility and stuff. Right now, we are just assuming that some, law students or maybe even the proper grown-up lawyers will use this tool and ask questions to answer, but to answer.
There's the cottage industry work on what are called trolley problems. These are things which essentially make it difficult for you to ascribe a responsibility. For example, in this case of the intersection, what if it was the case that there was a car behind the ego car, and it was clear to the ego car looking at the rear view mirror that the car behind was also looking at this indicator and thinking, they'll go ahead. And because the ego car was going to be hit from behind, it went into the intersection anyway. Even though the ego car knew that the turn was not, the signal was actually false. So you can get into things where it's really hard to dissect the intent. I mean, again, the purpose of the agent does further this. The ego car doesn't want to get in from behind, hence enters the intersection. But this is these trolley problems really, I think, muddy the waters quite a bit.
Yeah, and you will see all this, the situation that you described is actually what we hope. I mean, currently we have asking possibilities to do that, to ask what would you do if there was a car behind you and following properties. That actually we can ask, and we could actually by having simply program of the car, we would see what would be the outcome, and then we can conclude more, right? But currently we can do this in ask if you write all this as a formula, but our big picture is that we will be able to have a GUI where you could actually just add additional car and provide the details. Yeah. So where I am, I'm talking about responsibility, and then we can actually here even describe what the questions could be. So what we assume if the car was reasonable, right? We will say if the other car didn't signal, then we assume that the reasonable car would wait actually. No, then the ego car would have waited, because since the other car did not signal, that means the other car wants to go straight, so I have to wait. Then again, if the ego car had the right of the way, because it's a reasonable car, it would just continue. And then reckless car, reckless car is the one that independently what is coming is just moving. So you can again describe this as if something has happened, then that would be the outcome. And then if car is pathological, again, the car, we can describe this strange behavior will be like if the car did not have a single, okay, there is too many negations, but what we try to say is like if the car had the right of the move, but there was no other car, it would wait until it has practically something to crash into. So we can, all these problems we can actually explain as a counterfactuals. And
so is pathological really that its behavior is arbitrary? And
no, pathological, we assume that it's really what we find pathological, but what we assume is just the car who wants to do maximum damage, right? It just wants to crash.
So in this case, the last sentence says the ego car would have waited.
Yes, because there is nothing to crash, right? The ego car has right of the way, so it will really go. But since it's pathological, that means no one will crash into it, so it will wait until something else that they can crash into. So, I hope there are no such cars on the street, but we just kind of try to model this behavior. So where we are now. So now we finally came to intentions, and I can also tell that was the first thing when we started to talk, and we had another professor from law school who actually, Gideon, who both told us we need to have formalization of intention. So this is what we are trying to do. So, here, and I will show you how you can actually say, how can we even talk about intention when it comes to autonomous agent, right? It's just computer program. And let's actually try to guide you towards this through the human, right? So I will say, if I want to say, what is first intention defined? It is, there is some long-term goal and which I want to achieve. And to achieve this long-term goal, I will have some medium-term decisions. For example, my long-term goal is to stay fed, so I will make pasta. But if my more long-term goal is to eat well, then I will order pasta right now. And now, if we kind of leave this aside and look at the intersection, it's like if my long-term goal is to get to destination safely, well, then I will wait to enter intersection, right? Because safety first. But if I just want to be fast, then I will just enter immediately to intersection. You see, I have intention and then I decide. And now if we think, let's try to translate this for the, from English to the word of autonomous agent. We can say the following, of course they're not persons, but we can say, if I want to maximize my reward profile R, then I will enter intersection. Because see, that's one reward profile, which I know that it will give me rewards when I'm driving safely. But the other, if I want to maximize reward profile R prime, that's the one which will be, where I will be rewarded to come somewhere fast, then I will enter the intersection. So we currently are looking through intentions through the autonomous agents through the perspective of their reward profiles that they try to maximize. And which brings me that now last thing that I want to tell about modeling is how do we actually then model counterfactuals. I told you that actually from our logging, log, we can actually see there is actually described where is some agent. So we can say, oh, look, there, if you look at the picture, we say there is my yellow car and the position Y. But what I can do in a counterfactual, I could actually say but what would happen if the Y was in the position, I don't know, 1.3? Even better, I don't even, because this is just a formula. I can also say what would happen if the Y was in this position between 1.1 and 1.4. So if you look at the picture, I don't know if you can see, Y now actually has a small little green box around it. So we know this is the question that we will say. We can look at here. There is a box. Yeah. So if you think what is counterfactual, it says leave the formula that you had exactly as it is. Just replace Y to be at the position 5.2 with some other constraints. So you can relax, you can put the other things. And because we are calling SMT solvers, which now currently I'm bringing finally SMT solvers, this is just a formula. Of course, we can do that cheaply. So now if you think what we are doing, now I think we have enough machinery to describe. So we have an agent code. We all agree that from agent code, we can derive some formulas, right? And then what you will do, you will ask queries. And queries are right now, as I said, encoded in the ASCII file because, we are still building GUI, but you will ask questions like what Shankar asked. What would you do, for example, if there was another car behind you? That's the question that you can ask. Or you will ask, and then you will run the SMT solver, which will say here's my code because, it's a formula. What would be the outcome? We get the outcome, and then we can say would agent do this? You will say, oh, it would never do, or it would always do, or I would give you a counterexample. What would be the outcome? And then if we think about when I started to put comparison with the human, I said, we already know something about human, right? And human has a history, or it doesn't have a history, which is a good sign, right? But, the human has a history, but then we ask, what would you have done in this case? What would you have done in the other case? So exactly is happening here. By asking this sequence of queries, and the queries will be exactly these counterfactuals, what would happen if what would be then? We're actually building and we can get output and we see what would be output. We're actually building like this sequence of what agent is doing, and we would have some sorts of explanation in behavior. So based on this, we can actually describe, like we ask human in the loop who better understands all this concept of responsibility, culpability, and intention to kind of classify this behavior. Would you conclude that this car was actually reckless, or would you conclude that this car has a software that is somehow, like reasonable, or is there something seriously wrong with it? So that's the big picture.
2 minutes.
2 minutes.
Sorry.
Okay, then we will have, okay, so let's actually just kind of quickly go through the how to convert programming to first order logic. I mean, what we are doing here is like something very simple. We just take symbolic execution and execute. And you know why is this very nice? Because, like when you do symbolic execution, you're also collecting path constraints. Path constraints means that already looking at the path constraints, you can tell somehow which are important things to ask in counterfactual or not. Because it's kind of, if your path constraints doesn't talk about something at all, then why would you add counterfactual? Because it's really irrelevant for here. So that's one thing. Then I will not go into all these details about formalizing environment, because I think I already described how it looks like, but also then when you ask behavior. So then this is again, it's just a Boolean, right? We will ask like, oh, will you behave? Will you move, or will you stay there, or what will you do next? So if you think about big picture, how the queries are looking like, what this goes like following, right? We have a program and we have our trace. So we can, if you want to take formal methods and verification, condition generation, what we will do, we have a trace, and where we are right now standing, that's our preconditions. We execute the program, and then we actually want to understand whether the program will indeed do behavior that expected that it will do. So you say like, if my car was here and there was car behind it and something else, and there is the program, will you move? And then they will say, yes, I would always move in such occasion. No, I would never move. Or, I will get some big example. Or even better, I mean, like you say, like, no, do the same, just change something. Again, counterfactual reasoning, we can see what would be the output. So here is the details to keep, to tell what we were using, like we use CLE and float. So thanks very much to Christian Kader and his student who was working on CLE float, but then actually abandoned it because it graduated. So all those things we actually had to somehow re-implement a little bit on ourselves. For answering queries, of course, we use C3. And so our reinforcement agents were trained because actually Q learning, but I want to rather maybe show you what we can actually do. So then we have decided, like, consider this evaluation part. Then we have decided, let's say, that we wanted to ask, like, is there a configuration of the signals, or that for the other car that will cause that ego car will not accelerate? So, like, we want to now understand the questions, and like that, if you're a lawyer, you want to say, like, value will not actually go into intersection. And when you ask, then actually we get like, this is satisfiable when, like, the other car doesn't blink. So, okay, then you say, maybe that looks reasonable for now. The car doesn't, like, blink. So, like, it will wait. But then you can also ask, like, but maybe the car is, like, boring, maybe just kind of constantly drives overly aggressively and tries to tailgate the other car. So we can again formulate this with the examples, putting the other car at a different position. And then we says it doesn't happen. And then even we ask to produce example, why does it happen? You see, the other car will turn. We can also say all this to the other car now turn. And we see that the other car doesn't just tailgate, but continues. So we can do similar things, like, again, this is not exhaustive. It's not, like, but we can, if you put the human in the loop, human can ask all these questions. It's like, look, based on what I have seen that the car will do, I conclude that this is actually a reasonable car. That the fact that it crashed initially, it was pure accident. And we can do exactly the same again for the bad car, right? This was our pathological car, where, like, since I'm kind of running out of the time, it would again do exactly, we would show that, like, what did we ask here? For is there an acceleration for which you would not go into intersection? Yes, you always go because there is a car, and you definitely want to watch that crash that car. But then is there a way that you would actually not run, that you would not invent, for which you would actually, practically what you're asking here, when will you wait? And then it says like, I will wait and if there is, the other car waits, and then I will just go and crash him the moment when the other car starts to move. So, and then you can actually, again, is this inclusive? Then you say like, look, those are two examples. This is pathological car. No, it's not. But we count that expert who is asking this question will ask probably more questions, or will actually continue asking questions until expert can actually derive their own opinion whether this is a good or bad car. So now, okay, let me conclude. So as I said, like, this is just the beginning. We want to understand better how we could actually understand what are intentions of autonomous agents. Also, like big picture is like how to establish this notion of culpability, of responsibility. There is still lots of work to be done. Like one of the things that actually, let me just tell you practically, all the things, all the beautiful videos that you have seen, this is already running. That was not a fake video. So we have, connection to CLI, connection to Z3, that's all implemented. And now, since it's really hard to believe that if you're a lawyer, that you will say, let me write. Okay, Scott could, but I'm not sure for his students if they could write SMT queries where we'll ask like, okay, and what would happen in this case? So what we currently want to do is really have a drag and drop GUI, which will just kind of say like, okay, add the car, add something else, and that you actually can easily model different scenarios. So that's if some of you recognize, this is the Ducky Town. It's very cute for modeling such environments. And another thing, since I am after all formal methods person, so my question is like, how could we actually find and synthesize number or finding interesting scenarios? So like, let's say if I'm looking at, okay, this is a simple car, right? Two cars crash. But if you have more complicated situation, how to ask the right questions. So I'm kind of thinking if we have already all this machinery, which is like, take the program, derive symbolic execution. I mean, just look at the trace. You will understand why you ended up in a certain case. Then take this and try to generate, even be more helpful to the user, kind of say like, see, this is problematic scenario. Try to see which of these options you need to modify. So that's like that I'll definitely be interested in how to synthesize better questions. So I'm out of time, so thank you, and thank you for paying attention, and I'm happy to answer questions if there are more.
In the interest of time, we have to move on to the next speaker, but thank you, Ruzica.
Thank you. Thank you, Scott. Bye-bye.
Yeah, thank you, Scott. Let's move on to our